Before we dive in, let's establish some ground rules. The first of three is the fluids we are working with in these demonstrations, we're assuming are incompressible. That means in order for the volume to change, the mass must as well. The second one being, our fluids must be in laminar flow, which is when the fluid is perfect and it's perfectly consistent in its flow. Finally, our fluid must also be perfectly not viscous. That means it's the opposite of honey. Now, in order to explain the floating ping pong ball with Bernoulli's equation, we should probably start with this. We need to explain why when my thumb moves quite slowly here, the water moves much more quickly out of here. To explain the phenomenon that we just saw, what we use is the continuity equation. So what that is we have, say we have a pipe here, and this pipe is 5 inches in diameter to start, and then it decreases to a pipe that is 1 inch in diameter. Now what this equation says is if there's fluid flowing in here, assuming those constants that we brought up earlier, those ground rules, assuming those are true, as this area decreases, the velocity that was once here then increases. If we put this into the equation, let's say the water is flowing at 1 meter per second. So if we put that into this equation, the continuity equation, what happens is we got area of 5 inches, well 5 inches squared, this pipe is area of 5 inches squared, times 1 meter a second to begin with. On the other side here, when the pipe turns to 1 inch squared, the new velocity, once we do the math, the new velocity, V2, then becomes 5 meters a second. Now we can change this equation around using simple laws that we already know to become mass over time. Mass 1 over time 1 equals mass 2 over time 2. And what that can tell us is if we have 1 kilogram flowing through here per second, that must stay the same through here per second. Now being that it's a smaller area, we see the same thing, that this 1 kilogram that may have taken up this amount of space up here will have to be spread out through here, thus increasing the velocity the same way we saw earlier. Now that's a different way to look at it, but that can bring us to Bernoulli's equation. Bernoulli's equation we can write down here real quick. So pressure 1 plus rho v squared, 1/2 rho v squared, plus rho g y equals the same thing on the other side. So what we can see here, if we apply the continuity equation that we saw earlier, and we have that same situation where we begin with the 5 inch squared area and we go to 1 inches squared in that pipe. All Bernoulli's equation does is add height as well as gives the velocity a kinetic energy, which makes it seem a little bit more complicated, but really in this situation we can just eliminate both of these because the height, the y, stays the same. And now what we're left with, the velocity we know increases on this side. We also know that the pressure has to decrease, which finally brings us to being able to explain the ping pong ball and why it floats. The point that we just established, as velocity increases, the pressure will decrease. If we have this ping pong ball and it's under a hairdryer, so we know that the ball will have lift just because this air resistance is overcoming the gravity at least. If I were to push the ball, this air travels around. It creates a sort of pocket. If we have the same scenario, we have the lift already, but the ball gets pushed to the side. Being that this velocity of the air is much faster than the velocity of the standing air around, this pressure is much lower, thus pulling the ball back. after it's pushed. And that does it. That keeps it here. Even if I tilt it either way, the ball will have less pressure on the side that it's going away from, which then pulls it back.